Did everyone see that? Yeah? Can you hear me? Yeah?
We can hear you and we can see it. Looks
Okay,
good.
excellent. Thank you. All right. Hello, everyone. Today I'm going to talk about some work that myself and a whole bunch of colleagues at CSIRO have been stuck into for quite a number of years now. Our latest project, sponsored by the GSQ, is called the Cloncurry Multi-Element Toolkit and Laboratory. And I just want to give a shout out to my collaborators down there. So the idea of this project is basically integrated geoscience. So what we're trying to do here, rather than trying to integrate data after the fact, we're trying to collect our data in an integrated way. So we're looking at the entire mineral system, but mainly focusing on about 25 deposits. We collect something like 50 to 80, maybe up to even 250 samples per deposit, depending on how important we think it is. And then we end up with a whole bunch of point samples, which are these little paleomagnetic cores. From each of these cores, we can generate a whole bunch of different data sets. So, and you can see these down the side here. So we're talking about remnant magnetization, magnetic fabrics, which gives us structural geology, susceptibility, density, chargeability, radiometrics. We get mineralogy from TEMA, so we get these lovely little mineral maps for each of our samples. We can get geochemistry, and we can also get hyperspectral. This generates a huge data set, and the great thing about this is it's all pre-integrated, so we can do a whole bunch of neat stuff with it. I guess the underlying principle that we need to use when collecting this data is we need to get a representative sample. And this is quite a good example here at Stara. You can see we've got 3 main drill holes which go from the footwall through the mineralized system into the hanging wall. We're sampling mineralization at depth. We're sampling it up a bit further here. We're also sampling along the ironstone along strike. So we're really trying to get a representative sample, and that's really critical. What we get out of this, so with the TEMA, the mineral mapping, and the Petrophysics, these 2 data sets together allow us to do quite a lot of different things. So by integrating the data in this way, we can generate lots of different toolkits. As you can see here, I'm going to focus on geophysical tools and petrophysical tools today. And the ultimate vision with this is basically that we want to use what we learn in this project to generate some simple things that people can do in the core shed using handheld tools. So for example, portable XRF, portable ASD, which would be the hyperspectral, gamma ray spectrometer, a sus meter, and some sort of basic scales which you can measure density with. Using a combination of these tools, you can most likely figure out quite a little bit more about what you're seeing. Today's objective is just simply to provide an understanding of the processes that control mainly magnetic signatures, and to a lesser extent gravity and radiometric signatures. So we're focusing on Cloncurry. So Cloncurry is world-renowned for IOCG mineralisation, but in fact, there's quite a diverse range of types present, including also iron sulfide copper gold deposits, VMS or broken hill type deposits, skarns, and carbonate hosted deposits. So these are mineralogically, geochemically, structurally, and geophysically very diverse. So just to look at the geophysics, here you can see this is just a simple plot of magnetic susceptibility versus density. There's 2 main trends on here. The one in grey is basically magnetite enrichment. So you can see along here deposits that are basically just enriched in magnetite, or parts of deposits that are enriched in magnetite. Osborne up the top here. And that's pretty typical of your Cloncurry IOCG type deposits. Along the bottom here, we're seeing an enrichment in basically hematite, pyrrhotite, or pyrite. So these are minerals that are very dense but non-magnetic, and you can have combinations in between. So Maronan has magnetite and garnet, so the garnet gives it added density. Monakoff has magnetite and barite, so the barite gives it added density. In terms of the processes that drive this, I see Tobias is online. He'd be pretty happy to see this. I'm not going to talk about this now, but I will talk about this at the next one on June 18, I think it is. So you can look at this as being governed by reactive transport. I'm not going to say any more about that, but tune in on the 18th of June. In a more simple way, you can think about the magnetic minerals as being controlled by gradients. So potentially redox gradients or pH, temperature gradients. So here's an example here, and this is basically a VMS system. And in this, the zonation of the metals is controlled by metal solubility at different temperatures. In the core of the system, you have barite, which is what you see in some IOCGs, incidentally. And outward of that, you have lead, zinc, and then copper, and then the distal part of the system is iron. And this kind of zonation is, I suppose, relevant to VMS and SEDEX and maybe SCARM type systems. So in thinking about how redox, for example, affects magnetic signatures, if you think about a deposit which has basically the same metal content but different magnetic minerals, at the oxidized end of the scale, you have hematite. So they all have the same gravity signature, but the hematite-rich deposit will have a very mild or potentially no magnetic signature. As you get more and more reduced, you get more magnetite, and your magnetic signature gets a bit larger and larger. As you get out to the very reduced side, you're basically precipitating pyrrhotite, so no oxygen in there. Pyrrhotite can be magnetic, and where it is magnetic, it often has remnant magnetization, which is what you can see up in the top left corner there, and in the right corner, sorry, in the bottom left corner, you can see there's non-magnetic pyrrhotite, and that will basically have very weak magnetic signature. So these kind of principles are relevant to a whole bunch of different deposits, and we're going to look at some examples of some maybe sort of weird, controversial deposits in the Cloncurry district, and just show you some of the zonation, I guess, within them. So this is Monakoff here. It was mined out, I think, maybe 2013, 2014, somewhere around there. What you can see here, you've got a stratiform magnetic anomaly, but it has a very weak magnetic signature in the distal parts, has a very strong magnetic signature in the core. And this is basically indicating that you're going from quite an oxidized assemblage into quite a reduced assemblage. So you're going from hematite-rich into magnetite-rich in the core. You're also getting, in association with this very magnetite-rich zone, you're also getting a very large density, but that's basically due to barite in the mineral system. You can see that here. These are the rocks, so these are the temescans down the bottom. You can see this sort of oxidized hematite-rich assemblage over here, so it's just quartz and hematite. That is basically sitting on the outside of the system. As you come into the more proximal zone, you're getting this stratiform magnetite, and this is basically just partial replacement of the siltstones that host the deposit. As you get into the core of the system, you have lots of magnetite. You have total fabric destruction, so it's completely recrystallized. You can see in the pink here is the barite. It's hard to know whether this is just the core of a sort of VMS type system or whether this is a later sort of magmatic overprint. But that's for the geochemist to figure out. So let's go and look at another one. This is Moronen. So Moronen, I guess, is thought of as a broken hill type deposit. And in this one, you kind of have the opposite effect. So you have these two huge magnetic anomalies sitting to the north and the south of the mineralization. And then you have a very or zero magnetic anomaly in the middle, in the saddle between these two magnetic anomalies. So in this case, what you're seeing very oxidized, in this case, magnetite on the outer part, and in the middle you're seeing pyrrhotite. And the pyrrhotite can have very high Königsberger ratios, as you can see in this little table here, Königsberger ratios of 62, but that's related to very low susceptibility, so it's not going to cause you a big magnetic anomaly. This is what the rocks look like. So again, you're seeing these stratiform textures on the sort of outer parts. So you've got this magnetite-rich, sort of garnet-rich, calcite-rich rock here. It's very, very, very magnetic. As you come into the middle, you're getting these calcite, pyrrhotite, galena assemblages. And again, similar to what you're seeing at Monakoff, you have completely recrystallized textures here. So what you're seeing here, potentially you could say it's consistent with a metamorphosed VMS type system. You could potentially say it's a skarn. It's possible that the core of this system has just been partially melted during metamorphism. There's a lot of questions still to answer. But that's basically what's controlling the geophysics of this system. In terms of the mineral zonation, what you're seeing in the magnetic zonation is basically mimicked in the mineral zonation. So here you can see this is basically a magnetic model in grey here, and what we have over the top, we're basically mapping different shells using leapfrog. So on the left there, the red shells are mapping magnetite. You can see those big magnetite blobs to the north and south of the ore. And then basically the lead is running from the sort of proximal sort of iron-rich zone into the core of the system, and then the zinc and the silver are much more restricted to the core. So in this case, the petrophysics is related to the mineral distribution. Okay, I was talking about pyrrhotite a little while ago. Now, the thing about pyrrhotite, as I mentioned, it can have very high Königsberger ratios. So you can see here, I'm plotting the Königsberger ratio, and that is the ratio of the remnant magnetization to the induced magnetization. And you can see remnant magnetization is quite significant for some of these systems, so cantine, cormorant, and moronium to some degree. However, you can also see that there's pyrrhotite down here, so you have non-magnetic pyrrhotite as well. So it basically has zero susceptibility and low Königsberger ratio. And what it seems that basically the sort of lead-zinc-rich systems seem to be associated with the hexagonal or the non-magnetic pyrrhotite, whereas the copper-gold systems, for the most part, seem to have the monoclinic pyrrhotite. Just to show you an example, this is from Artemis. So you can see here, this is again just the susceptibility versus density plot. You can see almost all of the rocks here basically have zero magnetic susceptibility, and even where you do have some, 0.1 SI is still very low. And in fact, most of the magnetization within this system is sitting outside of this mineralized zone. So the magnetic anomaly here is sort of part of the distal part of this system. It's occurring structurally toward the surface from the mineralized zone, and it's basically modeled here. So what we're seeing is the hexagonal pyrrhotite there. And in fact, if you run a mag survey over this at 200-meter spacing, you won't see any magnetic anomaly over Artemis. It's only the 50-meter magnetic data in which you can see. So the other instance where you can get quite a lot of pyrrhotite is the sort of iron sulfide copper gold systems. So I guess Eloise is probably one of the main ones we think of. But we also see calcite pyrrhotite assemblages in Cantine, Moronium, Artemis. So we just spoke about Moronium and Artemis, but Cantine as well. Canting's more of a copper system. We also see albite, pyrrhotite, chalcopyrite, titanite assemblages, and we see these at Cormorant, which is up north of Ernestina. Now, in terms of looking at the remanence, this is of geophysical interest because we might be able to use remanence to actually identify this style of mineralization just based on magnetic data alone. What we found is that the remanence directions are more or less all pointing upward. And it seems that they've all been reset during the intrusion of the Lakeview Delaware. This is unfortunate because if they're basically in any other direction, we would be able to distinguish them from the Earth's magnetic field. So Earth's magnetic field also points up, but slightly more to the north. So unfortunately, we can't distinguish the remnants in these from the Earth's inducing field very easily. But there is another interesting geophysical aspect to some of these pyrrhotite assemblages. And this is also from Cormorant here. So this is just looking down. It's basically just a downhole log. We've got the geology over on the left. So you can see you're going from basically country rock into albite, magnetite, titanite assemblages in blue there. And that's then transitioning into albite, pyrrhotite, titanite assemblages in the yellow there. So basically, you've got a redox boundary from the magnetite dominant assemblages into the pyrrhotite dominant assemblages through here. You can see there's a huge drop-off in the magnetic susceptibility. This line here basically goes from the maximum right down to 0. And if you look at some of the geochemistry, what you can see is you've got sulfur dropping out across this redox boundary. You've got iron dropping out on the more oxidized side. You've got copper dropping out on either side. And most importantly, what I'm about to say next, you've got uranium dropping out also on the oxidized side. So are the redox boundaries controlling copper? Well, they certainly seem to be controlling uranium. So I guess what I'm trying to say here is this redox boundary is controlling where the uranium is dropping out. You can see that in the radiometric data, the regional radiometric data. So here you can see this is from Canteen South here. You've got a huge magnetic anomaly, so that you can see that in the shading here. Under that, you've also got this blue zone, which is basically a uranium radiometric anomaly. And they match 1 to 1. So here, the radiometric signature is correlated with the magnetite alteration within this system. So part of this project, we're doing radiometric data analysis. And this is just a plot of all the samples we had as of a bit earlier this year. And what you find is that about 5% of samples have highly elevated uranium relative to thorium and potassium. What these have in common, they're basically all sort of IOCG, ISCG deposits. They all contain carbonates, they all contain apatite, which is potentially a radiation trap. Some contain allanite and celestite, which are uranium-bearing minerals. But I think based on discussions with John Walsh, all these samples sit in basic redox gradients. So we're seeing magnetite and pyrrhotite in a lot of these samples. We're seeing a variety of different titanium minerals, and we're seeing a variety of different feldspars. Another interesting thing is there isn't always magnetite and hematite present. And I think that's sort of in contrast to what we thought we knew. So conclusions, alteration of structure, control petrophysics. Magnetic mineral precipitation is controlled by either temperature, pH, or redox gradients, or reactive transport, as I'll discuss next time. With uranium anomalies, we've probably seen them in association with chemical gradients, changes in redox. They can potentially map prospective horizons. And I think you can use some of these principles to differentiate prospective targets from non-prospective targets, both in potential field data or regional data, and also using tools in the course. And that is it. Thank you.
Thank you so much, Jim. We'll take questions for Jim if we have any. I think you've bamboozled everybody.
Yeah.
Oh, hang on. So Richard Blewett is asking, it's not entirely related to the topic that you've discussed, but are you doing a full element suite? And he's thinking about in a critical minerals context.
You're talking about geochemistry. Yeah, ask Vlad. Is Vlad online?
Vlad is online, and I guess as for the GSQ, we can answer that as part of this collaborative relationship with CSIRO for this project, GSQ and Vladimir Lisitsin's team are handling the geochemical side of the project. And I know that they are definitely doing a full suite of elements. So in answer, Richard, yes.
Dodge that one.
All right.